problems?
What's that?
Last couple of problems on our online homework?
This time or next time?
This time.
This time?
Saturday?
The ones from Saturday.
Yeah.
Yeah, we finished.
I don't think we went over anything.
Let's look at them.
We decided on.
So I know that a number of people struggled with one of them, which I thought was, I think the question was, what's I? There was a resistor here, plus, minus.
Yeah.
A resistor here, plus, minus. That was intended to be a really easy problem. Alright. So, we know a couple things. We know Kirchhoff's current law, the junction law. What does that tell you about the junction?
What goes in must come out.
What goes in must come out. Alright? And we know Ohm's law, which tells us that if the voltage across the resistor must be equal to the current through it times the resistance. Then the current goes into the positive or into the negative?
In the positive.
Into the positive. So the current's flowing through that resistor that direction. It's flowing through that resistor in that direction. Does that make sense so far? What is the current through that resistor? Well, we know that from Ohm's law, V equals IR. What must I equal?
V over R.
So we can find the current through that resistor, we can find the current through that resistor, and then the current in must be equal to the sum of the current out. Does that make sense?
Let me go over the second part of that question.
All right. Which number was that?
I can't understand the
Number one. Like the very first one.
This one right here?
No, something like that.
Oh, there it is.
It's the first one I got stuck on.
All right. So this one, how do we solve it?
Do the
Parallel.
We can
Parallel
combine,
to
these
30,
two
35.
have the same voltage across them, so they must be in parallel. So we can combine them into a single equivalent resistance. Then that equivalent resistor is in series with the 42. So then we combine the 42 with the equivalent to now get a single equivalent here. Now that single equivalent is in parallel with the 40. And you found the equivalent resistance. Questions? This one, which ones do we go after first? This 10 and the 30, they have the same current going through them, so they must be in series, so we can turn them into an equivalent 40 ohm resistor. Then we have a 40 in parallel with the 60, because now that this equivalent resistor has the same voltage across it as the 60 ohm. So we combine those two parallel resistors, and that equivalent's in parallel with the 10. We're done. This one bothered people.
Yeah.
All right. What's the relationship between the electric field and the potential? The rate of change of remember, what are our two units for electric field? Newtons per coulomb and
Volts per
volts
meter.
per meter. So the rate of change of your potential per meter gives us the electric field. So in the x direction, the electric field will be the negative Is that negative 50 or 50?
It's great.
50x minus 100. And I'll change that to a power. And that's volts. When I take the derivative with respect to x, the units become volts per meter. Derivative of 50x is 50. Derivative of negative 100, so x to the negative 1, it will be negative 1 times x to the negative 2. Then how do we find x, the electric field at 1 meter? We have to substitute 1 for x in that derivative. What about at 2.3 meters? We substitute for x. You guys have graphing calculators, right? And you can graph this and visualize what the potential looks like, and then you should be able to, the workbook problems are just supposed to help you try to visualize the relationship between the electric field and potential. Any questions about that one? All right, so this one, I think some of the people had problems. I thought I warned you, but then I emailed you to use the table in the book. And then same with the next one. All right. Current density. Okay. What is current density? It's not a volume density, it's actually a surface density. So you think of cutting the wire, right? Cutting through the wire, finding the cross-sectional area. You divide the current by the cross-sectional area, that tells you the number of amps per square meter.
I was mostly just confused by like the 100 watts and 0.8 whatever amps. I wasn't sure like how to deal with those numbers. I guess I wasn't sure what the.
Well, one of the wonderful things about real life is we always get, I find, and I'll tell you that I see this in my job all the time. I get one of two situations. Either I get too little information and I have to guess what I need. Because my boss really doesn't care. He wants an answer now, or tomorrow. And sometimes I have to guess what some of the parameters are. And just, I'll do what research I can, and then I have to make an educated guess. Or I have an abundance of information, most of which is useless or conflicting. So really sorting out what you need and what you don't need is important. So when we are asked for current density, we need current per area. Power, in this case, is irrelevant. So knowing what you don't need is a really important skill, but it does make the problems a lot more difficult. I do find that when I give students extra information, they do struggle. It makes it harder to figure out what's going on. You have to think about the phenomena a lot more. I do like to do that on the test though, occasionally. So it's good to see it the problem because I do throw that at you in tests also. I will give you extraneous information. You need to know what's useful, what isn't.
How do we get the second part? The electron current.
What is the electron current in the filament? You assume that there are so many coulombs per second, right? So how many coulombs? So you go from amperes to coulombs per second. What's the charge on a single electron? Right? How many electrons are in a coulomb? So it's really a change in units. Any questions about that? There's the one we just talked about. So 6/2, what's the current here? 3 amps. Then the current 10/5, 2 amps. How many amps are coming in here? Must be 5 amps coming in. So here's our current that we're asking about. The answer is 5. Is it going towards or away from the junction? Towards. It has to be going towards the junction because the current in the other 2 resistors is going out. So on the circuit, this I here is for the third leg. The pluses and minuses tell us that the current is going away from the junction of the two resistors, so then in the third leg the current must be going in. Does everyone see the reasoning? What do we do on this one? There's two batteries.
So one of them's got 9 volts going one way, the other's got 6 volts going
A lot of you can see that if you have 6 going up here and 3 going up here, there must be about 3 volts going that way. But let me show you the disciplined way to apply Kirchhoff's loop law. That's 9 volts, isn't it?
Yeah.
Now we're going to mark the positives and negatives everywhere we can on this surface. That's very key. Now I can guess the direction of the current. If I guess it wrong, I'll get a negative number. But I'm going to guess the current comes from the 9-volt battery. What are the markings now if this is I? Is this the positive and negative, or negative and positive? Positive to negative. Now I'll start my Kirchhoff's loop law here. What have I done? If I move from A to, say, B,
9 volts.
I've gone up or down?
Up.
Up, 9 volts. Now, when I go through the 30 ohm resistors, do I go up or down?
Down.
Down, so I put a negative sign. And what's my potential drop? It must be I times R. Now I go across the 6-volt battery. Am I going up or down?
Down.
Down from positive to negative. So I have a negative 6 volts. And then I'm back to where I started. So that's equal to 0. The 9 minus 6 is 3 volts. Minus I times 30 ohms equals 0. Or I times 30 ohms equals 3 volts. I can divide both sides by 30 ohms. This is a good warm-up for what I want to talk about in class. So what do I do to apply Kirchhoff's loop law? I assume the direction for the current. If I've gotten a negative number down here, that means that the current's actually flowing the opposite direction. I make sure I sign the negatives and positives on the batteries. Based on the current through the resistor, I assign the positive and negatives. If I've got a negative 1/10 of an amp, that means that these are backwards. Any questions about that? There's 2 ways to solve this one. The first way would be to just solve this just the way we did. So you put positive, negative here. Kirchhoff's loop law, let's start at A again. What do we do? up 15, down I times 10 ohms, down I times 20 ohms. And we're back, we start at 0. So let's see, we can say 15 volts equals I times 10 ohms plus 20 ohms. Divide both sides by 30. We find out I equals a half amp. What's the voltage across the 10 ohm resistor? I times R would be a half times 10 is 5 across the 20, 10, so we go up 15. What would be the voltage from A to C? The voltage across this is 10 volts, isn't it? So from A to C would be positive 10 volts. What would be the voltage from C to B? The voltage across this is 5 volts, but going from C to A, we're going
Negative.
in the negative direction, right? So it would be a negative 5 volts. What about from this point, from, let's call this D, to B? That's the same as A over B. Again, that would be negative 50. B over A would be positive.
How did you get the 10 on that side? Sorry.
What's that?
How did you get the 10 on the right hand side?
Ohm's law, B equals IR. So our answer was half an amp times 20 ohms.
Oh, okay.
10 volts. That's encouraging. We go up 15, we go down 5, we go down another 15, we're back at change of 0. Now what would be the other way to find this? If this 10 ohm and 20 ohm resistor, are they in parallel, series, or something else?
Series.
Series, so the equivalent resistance then would be 30 ohms. $15 volts. Now Kirchhoff's loop law is pretty straightforward. 15 volts minus I times 30 ohms equals 0. We'll still find that I is that amp.
Out of curiosity, is there another option? You said parallel series or something.
What's that?
Is there another option for resistors? Can we find something that isn't parallel?
There's another analysis technique called Thevenin's equivalent,
Okay.
where we can resolve any resistor battery circuit to a single battery and resistor. We won't learn that in this class. It's a very powerful tool. It's got an analog which is called a Norton, which is a current source in a resistor. If people want to come by and talk about those, I'll be glad to do it. We don't need it for this class, but if you go into electronics, it's just a very, very powerful tool.
So when you take a point and you go in whatever direction and you find that there's a potential difference of -5 going that way. So it doesn't matter which direction you go, just one way is obviously sometimes more.
You mean in terms of your loop?
Like you started at C and you wanted to find the potential difference between C and D, it wouldn't matter which direction you went, you'd get the same answer.
Oh, great question. So our current here is half an amp, right? So if we look down across this resistor, the answer is we've gone down, right? 10 volts. So we're 10 volts higher than this point. I times half an amp times 20 ohm. What if we went this way? Our voltage across this So we go up a half a volt, or excuse me, up 5 volts, and then down 15 volts, right? That means we've had a net change of, again, 10 volts. We're going from A to C, we've gone up 15, down 5 for a net change of 10. And by Kirchhoff's loop law, it shouldn't matter which way you go.
Can you use the loop law for like parallel?
We can use the loop law for parallel sections. Plus, you've gotten to right where I want to go to start this lecture. But before we do that, I have a quiz. I think you'll like this quiz. You've been following this. I'm really hoping that we do very well.
That makes me nervous. The pressure's on.
All right.
I'll be the one person getting all of them.
Are we ready? I promised you I wanted to know if you remember. No, I don't want to take it close. 3, 2, 1. I like the quick confidence. That that is a battery, folks. Shot. Three, 2, 1, and what? We've got all 5 of them. That is a capacitor. 2 plates. Didn't I even promise you I was going to give you circuit elements on this quiz? Okay. Capacitor, 2 plates. If I double the area of plates, what happens to the capacitance? The capacitance increases. So if I put capacitors in parallel, what happens to the amount of capacitance? Capacitance goes up. It's not like resistors. You may put resistors in parallel, the resistance goes down. What if I put capacitors in series? What will happen?
It goes down?
The capacitance goes down. So they're just the opposite of resistors. All right, what is this thing? That line. 3, 2, 1. There we go. All right. Three, 2, 1. There we go. I used to see the electric machinery down at Idaho. They have these big machines. They're very big. They have 400 volts, 100 amps. I mean, really. When they open the switches like this and they're not supposed to, these nice green arcs, right? Smell the ozone. I used to have the fire department come for the first lecture and teach CPR to try to convince them to be careful. I only had one have to go to the hospital with an ambulance.
That's pretty good.
Well, put his hands right across the heart bolts. Yeah, that was all right. This lab is I like labs like they're much less, don't worry about you killing yourself. Let's put it that way. All right. So, the question was, and it could have been a plan, what do we do if we have parallel resistors? So, there are two ways to solve this. What's the easy thing to do? We could find, if we wanted to find the current from the battery, I would find the equivalent resistance of the two. Then I'd have a single loop, right? Because then I have
6.
But now, it's to determine the current through each resistor and the current delivered by the batteries. What do we know about R1 and R2 just looking at this circuit? They're parallel. Excellent. What else do we know?
They're not equivalent?
Since they're in parallel, what do we know that they share? Do they have the same current through them?
They have the same
No.
voltage.
Right? The current comes from the 9-volt battery. It will split. You have some current going this way, some current going that way. But the current going through the 10 and 15 ohm is not the same current that's going through the 10. If they're in series, the current has to be the same. So what do they share then if it's not the same current? Same potential. There's the same voltage difference across them. So the easy way to find this would just be to look at, we could do a Kirchhoff's loop law. And just say, the way I would do this is in my head I would take a Kirchhoff's loop around first loop I would take is this one right here. Just go right around like that. What would that loop look like? Let's do one other thing. Let's label these currents. There's now 3 currents. Is this the same current going into this junction as going down to the...
No.
So I'm going to call this I1. I'm going to call this I2. Is that really going to be the right direction for I2? No, I guessed it wrong because I'm not a real good at this. But life will come out. I want to show you that it works. And we have I3. So for loop 1, let's see. Then we need to put our pluses and minuses. The way I've drawn this, this will be positive and negative. The current goes into positive. And the way I've drawn this current, this will be positive and negative. Now what we're going to do is end up with a negative potential for this, so that I'll say that I've got it backwards. Now for loop 1, what does Kirchhoff's loop law look like? We start here, what do? We go up 9 volts, that's positive. Then we go along this wire, what change in potential do we have? Say, let's call this A, B, C. What change in potential from B to C?
There isn't one.
None. What about from C to D?
Yeah.
It'll be I3 times 15 ohms, right? And is it positive or negative? Are we going up or down?
Down.
Down. Minus I3 times 15 ohms. And then we're back to where we started, so it's equal to 0. If we do a little math now, we can see that I3 will be equal to 9 volts divided by 15 ohms equals 3/5, 0.6 amps. We can do something very similar with a big loop. Okay. Call that loop 2. So this loop goes from the 9-volt battery through the 10 ohm and all the way back to the loop center. So this is loop 1. Loop 2, what do we have? Up 9 volts. Then from B to C to E, no change. And then are we going up or down through this 10 ohm resistor? Up. So that will be plus I2 times 10 ohms equals 0. So I2 equals negative 9 volts over 10 ohms equals negative 0.9 amps. Oops. I guessed the direction wrong. It's not a panic, just that that's what happens when I make a mistake. I guess the current doesn't, all like statics, right? So, the current really is down through this. The voltage is really positive here and negative there. So if I multiply the negative 9/10 of an amp times 10 ohms, I would say I get a negative 9 volts here, that designation. Or if I change the correct orientation, it's positive 9 from bottom to top. Any questions about what happened with the negative? I just want to show that because sometime with more complicated circuits you may make a mistake, you get a negative answer. In this one where it's obvious, it's really straightforward. So, but that's kind of the hard way if I wanted, how do I find out what the current is? I found out what the current is through the 15 ohm. I found out what the current is through the 10 ohm resistor. How do I find out what the current is from the battery? We can use Kirchhoff's junction law. It goes into is half equal to it goes out as, so I have I1 plus I2 coming in, right? Must equal I3 going out. I1 was
We're solving for it.
we're solving for I1. So I1 therefore equals I3 minus I2 equals I3 with 0.6 amps minus a negative 0.9 amps equals 1.5. So again, the negative sign works out. It tells us, I guess, that this direction was wrong. As long as we're careful with our math and we keep track of that negative sign, we'll be okay. If we found the equivalent resistance of a 10 ohm and a 15 ohm, what do we get? We get 6 ohms. 9 volts across 6 ohms is 1.5 amps. Any questions? That one's fairly straightforward. It becomes more interesting when we get this. Now what do we do?
More loops.
We'll do the same process we just did. Define I1, I2, I3. We can apply Kirchhoff's current law. We can apply Kirchhoff's voltage law or loop law. And we can solve this. I'll give you a second to work on it. This time, these are probably the correct directions for the currents. I'm rather certain from the highest volt battery, the current's coming out. It's probably going in this direction for this one, but we won't know for sure. Possible that this is enough higher voltage that current's actually flowing down through that battery, in which case that battery would actually be charging. Let's see. What have I forgotten to do on my circuit diagram? The what?
The resistors, positive and negative.
Yes. Mark these. Please, please. It helps immensely in getting the right answer. Good. All right. Kirchhoff's loop junction law here. We know that, oh, I labeled these differently in the 853.
You also set R2 with different poles.
What's that?
The picture has R2 with different poles. The right.
Oh, I've got those wrong. That needs to get fixed.
Wait,
So those are a
what?
mistake.
Oh.
That's unfortunate.
Just pretend.
So in the notes, I will fix that and repost that. So, we will treat this as two loops. There are two choices. One loop could be here, and I could do another loop there. Or I could do a third loop all the way around the outside. Let's do loop 1. We go up 9 volts, down minus I1 times 4 ohms, down I3 times 15 ohms. That's loop 2. Can we start at the bottom of the battery again? I tend to like to start at the bottom of the batteries. We go up 6 volts. Down 2 ohms times I2. Down. Now I have a problem. I have 3 unknowns, I1, I2, and I3, and I only have 2 equations. It works out if I do another loop, it's actually the information's embedded in these and I don't get any new information. So using Kirchhoff's loop law won't help us to get our third equation. But I have written it up on the screen. We know that goes into us, half the equals out, goes out as up here. So the current's going in, I1 plus I2 has to be equal to I3. What I would do from here is I would substitute for I3, I'd say I1 plus I2, put it here. I would put I1 plus I2 up to here. And I've gotten rid of one unknown in these 2 equations. Now I'm left with 2 equations, 2 unknowns. Everyone see how we applied the loop laws and the junction law? Not, I promise you, this will be a skill that you will see a week from, 2 weeks from Wednesday. You will see a problem that looks like this, I guarantee you.
Do we just, for the I1 plus I2, just substitute in for I3, or are we just adding I1 times 4 ohms plus I2 times 2 ohms?
This right here,
Yeah.
you just put I1 plus I2 here, and then you'll have to multiply both times 15 ohms.
Oh, times 15 ohms.
I1 plus I2 here, again, it's going to be multiplied times 15 ohms. Then, this is an equation in I1 and I2, this is an equation in I1 and I2, you have 2 equations, 2 unknowns. It's pretty straightforward. I will need to remember to fix that. Sign it there. All right. Any questions about this?
As well. Post that, can you post the answer along with that?
What's that?
When you post this, can you post the answer along with that? So-
All right, I'll do that. You want to see the algebra? Yeah. All right, I'll fill it out. You don't want to spend the time in class doing algebra. Capacitors. Because capacitors are very, very mysterious devices. But they're so simple, and they're just plates. But what did they do in circuits? When you first put a capacitor in the circuit in lab, what did it look like? Did it look like an open switch, a wire, a resistor? When you first took and built your capacitor circuit in lab, I think you built a circuit that looked something like this. You didn't really have a switch, you just connected the wire. When you first closed the switch, what happened to the light? It lit up, didn't it? Yeah. And that, what was happening inside the capacitor? Electrons were getting on, forming on one side, and positive charges were forming on the other side. In terms of our circuit model, really we just know electrons are leaving one side and adding another. Well, we can think of positive charges building up on one side and negative charges building up on the other. At first, there were no charges built up, so there was no electric field, there was no potential difference there, was there? So if we did Kirchhoff's loop law, we had minus plus, whatever that voltage is. Then what voltage drop was there across the capacitor? What potential difference was there across it? 0, because it wasn't charged. So, from the perspective of the circuit, all we saw was the resistance of the light bulb when we first switched it. So when we first close a circuit and the capacitors aren't charged, what does the capacitor act like? Like it's not even there, like it's a wire. After a long time, what happened to the light bulb? It turned off. Enough charge built up here that there was a voltage equal to, what's that voltage across the capacitor? Became equal to this voltage here. If we look at it in terms of Kirchhoff's loop law, we go up that voltage, we drop that voltage. How much voltage is there to drop across the light bulb?
0.
0. There's no current flowing anymore. So after a long time in a DC circuit, what does the capacitor look like? An infinite resistance, doesn't it? No current flows through it. Even a large resistor would let a little bit of current through. But after a long time, the capacitor looks like an open circuit. So, what I want to talk about today is, just very briefly, is how do we analyze those circuits with capacitors when we first close the switch and when we have let it sit for a long time. When you first close it, if the capacitor isn't charged, it acts like a short circuit. When we first close it, the instant we close it, right there, right after we close it, what does this look like? It looks like a wire. We'd solve this circuit exactly as if it was a wire, and that's how the circuit starts.
Is there a way to determine like its resistance over time?
Well, what we know is the capacitance is what? The charge for the voltage. So if you want to know the voltage, that will be the charge divided by the capacitance. So what you have to do is find out what the charge is. This is tomorrow, this is Wednesday's lecture. But what's the charge? We know that I is equal to dq dt, right? So what is q? See, let's multiply by dt, and then petition shutter, integrate, and we have, oops, where this q equals the integral of I with respect to time. So, if we integrate the current going into the capacitor, we can know what the change in charge is. Once we know what the charge is, then we can find the voltage. Forget that until Wednesday. That's what we're talking about. What we do know, though, is at first, when there's no charge on it, what's the voltage across the capacitor? There's no charge. The voltage is 0. It just acts like a short circuit when we first close it. After a long time, what do we know? It acts like an open circuit. Do we know, is the voltage 100 volts in this circuit? Yeah, probably not, because it's a little bit more complicated than just one loop. But we do know one thing. I don't know the voltage across that capacitor after a long, long time, but I do know something about the current. If it's been a long, long time, what's the current through that capacitor? 0. So, what's the current going down through the 10 ohm resistor? 0. So what do we know about the current going down the 40 ohm resistor? It must equal the current going into the 60 ohm. So the way we analyze this circuit, it's been a long, long time. know that I1 has to equal I2 plus I3. If it's been a long, long time, what does I2 equal? 0. That means that I1 must equal I3. If I do a Kirchhoff's loop law around this path, I have 100 volts times I times 60 plus I times 40 equals 0. This looks like an equivalent 100 ohm resistor. With 100 volts across it, what does I1 equal? 1 amp. Equals I3, 1 amp. So we'll have what is our voltage drop or a potential change across the 60 ohm resistor? There's 1 amp, 60 volts, right? What is the voltage across the 40 ohm resistor? One amp times 40 ohms or 40 volts. So we go up 100 volts, down 60, down another 40, we're at 0. Well, what's happening over here? What's the voltage across this resistor now? Remember, this has been after a long, long time. What's I2? 0. What is the voltage across the capacitor? Let's see. Let's let this be our reference down here. What is the voltage across the 40 ohm resistor? 40 volts. If it's 40 volts from here to here, what's the voltage from here to here?
40.
40 volts. There's no voltage across the 10 ohm resistor because there's no current through it. So, what's the voltage across the capacitor?
40 volts.
Must be 40 volts. So, we close the switch, we wait a long time, after a long time there's 40 volts potential change across the capacitor. There's no longer any current flowing through it. The circuit is steady. There's 1 amp flowing through the 60 and down through the 40 and back into the battery. We can take Kirchhoff's loop law this way, or this way, or this way. It all works. Kirchhoff junction law works here. But the trick to analyzing it was after a long, long time, the current through the capacitor is 0. When it's totally discharged, we know that the voltage across the capacitor is 0. So in terms of thinking about the circuit, when we first close the switch, the capacitor just looks like a wire. When it's been a long, long time, it just looks like an open circuit. We've got 1 or 2 minutes to let that thought settle in a little. Is it? What I haven't talked about is real batteries, and I don't want to start that with 1 or 2 minutes. Let's quickly look at just a single, like, capacitor and resistor. The capacitor is completely discharged, and I close the switch. Let's say this is 10 volts, 5 ohms. What is the current when I first close the switch? How much charge is built up across the capacitors? 0. So there's 0 voltage across it. Current can go through it. If we look at the loop law, we go up 10 volts, no change, down I times 5 ohms. What must I equal for this loop to have 0 change in voltage all around it? 2 amps. So initially the current is 2 amps. After a long, what's the voltage at that instant across the capacitor? We have 2 amps flowing through it. But there's no charge built up, so the voltage is
0.
0. There's 2 amps through the 5 ohm resistor. What's the voltage across it? 2 times 5 is
10.
10 volts. Plus 10, no change, down 10. After a long time, what is the current through the capacitor? 0. What's the voltage? Now, if there's 0 current through the capacitor, what's the current through the resistor?
0.
0. So there's no voltage across there. We have plus 10 volts minus the voltage across the capacitor. Minus 0 amps times 5 ohms. 0. The voltage across the capacitor must be
10 volts.
10 volts. Does that make sense? Really not as bad as it looks. All right, see you Wednesday.